Okay, let's look at techniques for solving systems of equations. Um, in the next part of the textbook, it talks about elementary operations. There are certain elementary operations that can be performed on systems of equations to produce equivalent systems. That means a different set of equations that has exactly the same set of solutions as the original set. Um, so we're going to use these elementary operations to actually produce a simpler but equivalent um, uh, system of equations that we can easily solve. So the elementary operations that we're allowed to perform are we can interchange two equations, we can multiply one equation by a non-zero number, and then the third one is the most complex. We can add a multiple of one equation to a different equation. So, and this maintains the equivalence. This leads to a theorem, a sequence of elementary operations performed on a system of linear equations. The resulting system has the same set of solutions as the original. But we're going to go through these operations and as striving to find a system that has a particular form that makes it really easy to solve the final system of equations. Now, actually, instead of working with the linear system of equations, we're going to work, the notation is just a little simpler, to work with the augmented matrix, and their corresponding set of operations that we can do on the matrix that correspond to the elementary operations we can do on the system of equations. We can interchange two rows, multiply one row by a non-zero number, and multiply and add a multiple of one row to a different row. So let me work through an example to actually um, illustrate the process here. So let me pull up the whiteboard. And again, this is in the section of the textbook on elementary operations. He has some examples in the textbook. I'm going to work through one of the problems as an example to illustrate. This is exercise 1.110. So from at the end of section 1.1 and then working through B. The set of system of equations is 2x plus y plus z is equal to -1, and x plus 2y plus z is equal to 0, and 3x minus 2z is equal to 5. Okay, so the corresponding augmented matrix is 2, 1, 3, 1, 2, 0, 1, 1, -2, and then -1, 0, 5 is the corresponding constant column. So I'm going to go through a sequence of operations here. I'm going to try to get the coefficient portion of the augmented matrix into upper triangular form, where all of the elements below the diagonal are equal to the 0. To the left and below the diagonal are equal to 0. So I will write down the corresponding operations here for the augmented matrix. So the first one I'm going to do is actually subtract from row 1 2 times row 2 and replace that row 1 with the old row 1 with that operation. So by doing that, I can see that I'll eliminate this first term in row 1. I'll have 2 minus 2, so this will be 0. Then I'll have 1 minus 4, or minus 3, 1 minus a -2, which is -1. I have to do the same thing with the constants. I'll have -1 minus 2 times 0 in this case, so -1. Okay. And then I'm actually going to do another operation here, replace row 3 with the old row 3 minus 3 times the old row 2. That's going to become my new row 3. I'm actually just going to copy down row 2. 1, 2, 1, 0. And again, I did that because I see I've got a 3 here. There's a leading 1 here. So if I subtract 3 times this row, it'll give me a leading 0 here. Okay. And then I'll have 0 minus 3 times 2. So that will give me a minus 6. Minus 2 minus 3 times 1. So that'll give me minus 5. And with the constant term, I'll have 5 minus 3 times 0. So that will actually result in 5. So this is the next form of the augmented matrix. Okay. Again, I'm striving to come up with a lower triangular form. So I'm going to swap rows 1 and 2 because row 2 has the leading 1. So 1, 2, 1, 0. That corresponding operation is just swapping row 1 and row 2. And then, so let me copy down the old row 2. And then I'll do one other operation here. I'm going to actually replace row 3 with row 3 minus 2 times the old row 1. The reason I do that is I see that'll get rid of this leading minus 6 here. So I multiply this row 1 by minus 2, I'll get a 6, and when I add those, it'll give me 0 here. So row 3 minus 2 row 2, since both those are 0 here. And then I've already said I know I'll get a 0 here. Now I'll have minus 5 minus 2 times minus 1. So that'd be 5 actually minus 5 plus 2, or minus 3. And then again, I'll have 5 minus 2 times 1, minus 2 times a negative 1. So that would be plus 2. So that'll give me actually a 7 here. I'm actually leaving out the line here that's part of the augmented matrix, but I think you can follow along. So now I've actually got the augmented matrix in upper triangular form, where all of the elements to the left and below the diagonal are equal to 0. So actually the corresponding system here is relatively easy to solve. I can use back substitution. The corresponding system would be 1x plus 2y plus 1 is equal to 0. So x plus 2y plus z is equal to 0. The next equation is actually minus 3y minus z is equal to minus 1. And then the last equation is minus 3z is equal to 7. So I can start at the bottom here and work my way up. I'll get z is equal then to minus 7/3. Now that I have z, I can take that value of z up into this the previous equation and solve for y. And then I'll have an expression for y. I can take my values for y and z back into the top equation and solve for x. And that method's called back substitution. And I can use that method, as soon as I get this into this upper diagonal form. I'm going to do a little more work with it though, and actually try and reduce it into just the coefficient matrix into just a diagonal matrix with just elements along the diagonal. So I'm going to try and here in the second row, that's got the second row has a leading term in the second spot. So I'm going to try and eliminate the 2 in the first row by subtracting a multiple of this row. So that corresponding operation here, I can actually do that by replacing row 1 with 3 times row 1 plus 2 times row 2. Okay. And you might argue, well, that's not really an elementary operation. That wasn't one of the ones we had. And actually, you're right. I'm combining two elementary row operations on the matrix. You can think of it as replacing row 1 with 3 times row 1, and then adding that new row 1 with adding 2 times row 2 to that new row 1. So this is actually a combination of two elementary row operations. But I see when I do that, I'll get 3 here. Here I'll have 6 minus 6, and I chose this operation to eliminate that term. And then I'll have 3 minus 2, or 1 here. And then finally, I have 3 times 0 plus 2 times a minus 1, or a minus 2. Okay. And for row 2, I want to eliminate the term that's above the minus 3, above the diagonal term in the third row. And I see that I can do that by, again, it's actually a pair of combinations. If I multiply this by 3, I'll get a minus 3 here. And if I subtract row 3 then to get a new row 2, it'll give me a 0 in this position in row 2. So I'll have 3 times 0 minus 0. Then here I'll have 3 times the negative 3, or minus 9. And then again here I would have minus 3 minus a negative 3 to get 0. And then here I'll have minus 3 minus 7 would be a negative 10. And then I'll copy down this last row, 0, 0, minus 3, and 7. Okay. Almost diagonal form. I need to get rid of the 1 that's right there. And I can do that by using row 3. If I multiply this row by 3 and add row 3 to it, that will actually eliminate that term. So let me clear the whiteboard here, and the next matrix I get will be 9, 0, 0, 1, and then I'll have 0, minus 9, 0, minus 10, and then 0, 0, minus 3, 7. So I just did 1. This is 3 times R1 plus R3, replacing R1. Again, that's really two elementary row operations, multiplying row 1 by 3, and then taking that new row 1 and adding row 3 to it. But now I've got my coefficient matrix in just diagonal form. And again, it would be easy to solve. I'm going to take one more step here. I'm going to actually take 1/9 of row 1 to replace row 1. So that will give me 1, 0, 0, 1/9. And then I'll take a negative 1/9 in row 2 to replace row 2. That will give me 0, 1, 0, 10/9. And then finally I'll take negative 1/3 row 3, and to replace row 3, that gives me 0, 0, 1, and negative 7/3. Okay. The corresponding system of equations would be x equal to 1/9, y is equal to 10/9, and then z is equal to minus 7/3 as the solution to, the solution to the system of equations is obvious when it's in this diagonal form. Again, this is the solution to the original system of equations that I started with. You can take these values back and substitute into the original system of equations, and that you'll see that this is in this case, the one and only solution to that system of equations that had three unknowns and three equations.